Hi, this is Tracky, Research and Practice. We are in part 2. We're looking at AlphaGo. AlphaGo was the product developed by DeepMind, and it became famous because it beat Lee Sedol in a 4-1 match on the game Go. And today we are going to learn how the search plus learning part gave rebirth to the reasoning era. Let's dive in. There are many things that we learned in the previous sessions on A-star heuristics, big O notation, and everything. What we are going to look at is how many things converge here in this part of the research. And one thing that we very recently looked at last week on Friday was the 3-pass read on how to read a research paper, and the PM pass on how to do a PM pass on a research paper. Yeah, and we did this on AlexNet and Word2Vec. This week we are gonna apply it on the AlphaGo paper. It was published as Nature 2016 and Silver et al. There are many people in the paper, including Demis Hassabis himself, the the brain behind DeepMind. Go was AI's white whale. Chess had approximately 35 steps anywhere to make, but Go had approximately 250 moves for every turn, and this was very challenging in itself to solve. While chess was solved with brute force in 1997, the same cannot be applied or could not be applied at that point in time to Go, which had 250 moves per turn, which was more than the positions that we could calculate. And it was definitely more than the number of atoms in the known universe. And we are going to look at how one move that AlphaGo made it very interesting. And instead of calculating everything, it learned to calculate only what matters, because it learned that in the game of Go, even if you had one extra uh, space uh, more than the opponent, you were going to win. So it learned that from intuition, and it kept the search to itself. Yeah, the one thesis that we are going to learn is AlphaGo didn't out-search or out-intuit humans. It fused the two things that we wanted very desperately. One, it looked at all the possible paths that it could take, and it pruned it. It didn't go after all those paths. That was intuition. And it used tree search to look ahead. Hey, if I go to a particular point, I'll calculate the probability of win there. And it said, let me go where the probability of win is very high. That is how it deliberated the whole process. Yeah, it learned which network to follow, and then it took or calculated the success rate at each of them, and then proceeded further. So that's how it did the learning and searching. And it didn't do them separately, it did it together. And why is it a 2026 paper to read? Yeah, today when we do a test time compute on large model reasoning, this is where this paper becomes very interesting. And this is the logic exactly applied behind your R1, DeepSeek's R1, or ChatGPT's O series models. And today we are going to look at some interesting parts. First, we'll go with the context, why Go was the white whale, and why it was hard to solve using hand coded uh, parameters to solve this, why brute force couldn't solve this. And then we'll look at two superpowers that AlphaGo gave us. One is a policy network, that is the learned intuition, and then we look at the value network, which tells us, hey, how do you learn judgment? How do you proceed further, or how do you further deliberate from a particular position? It also used MCTS, which is Monte Carlo tree search, and it learned to look ahead. Yeah, 4 steps to be very precise, and that helped it. How AlphaGo learned, we are gonna look at human analogy on how it learned the whole thing. Finally, we'll conclude with the PM pass. Hey, what do product managers need to look at this paper, and what does it give forward to us? Give forward to PMs when we look forward into the future. And that brings us to the first part, which is why Go was the white whale for AI. Yeah, it presented us two impossible problems at the same time. One, there were too many moves to search, and we didn't know what step to take forward or how to judge a particular position. So imagine the game Go. This is how the game looks like. It's a 2005-year-old game. It has two players playing on the opposite sides, and they are trying to capture as much territory as possible. Each each point, or where two lines meet, is a point, and it's like a territory which you need to capture from your opponents. So in the beginning there is nothing. Each player keeps a stone. Unlike chess here, in Go, black player begins the game. Black player chooses where to begin. He can place anywhere, and then the other player places the white, and the other places the other. The objective is that you either cover your opponent's uh, stones, as they are called, completely, surround them with no possible move to make, or you capture these wide open spaces in the outer territory. You could either do these, or you could come and capture your opponent's stones. That's what you do. The challenge is, there are 361 moves, or dots, which is 19 by 19, so 361 dots in the place. At any point in time you can put a stone here and make a move, and after that there are 250 moves that you can make at each turn of yours. Yeah, with that, the number of possible combinations that you get is increasing dramatically at a scale. Okay, so in chess, while we have 35 moves per turn, in Go it becomes 250 moves. Imagine you're standing at a crossroad, and there are only 35 roads to take. It's challenging, but you could take one. Imagine there are 250 roads that you can pick from. It becomes a very hard and almost impossible problem to solve. And this happens with Go very easily, because at each move you have 250 possibilities. After 3 turns we have 15,625,000 moves. Imagine a full game where you can make approximately 150 moves. That is 250 to the power of 150. It is greater than the total number of atoms in the observable universe. And brute force is hopeless in this game. Imagine you enter a maze which is infinite in nature, unlike this one. You have to take left, right, uh, forward, backward, one of the steps. Okay, in each of that step, you will have to calculate four moves. And imagine if it is infinite, how will you reach the dead end? So this presented a very big problem for uh, DeepMind's team. This was a very interesting problem. Okay, they earlier saw that in 1997 Deep Blue beat Kasparov. Yeah, it was with pure brute force search. It searched for thousands and hundreds of thousands of games that were played earlier in that same exact position, and it had a hand tuned evaluation saying that if I make this particular move, what will be the success criteria. Yeah, now this was impossible with 200 250 to the power of 150 moves. How can you make or hand code so many moves? Impossible. Yeah, in chess we can count the number of material. There are you had queen which has 9 points, you had rook which had 5 points, then you had knight which had 3 points. So in chess you can actually count what's my score and so on. In Go, you cannot calculate it from the beginning like that, and many a times the sacrifices can win. Yeah, you have to position for quality which is holistic in nature and not additive. You can't just add saying that, yeah, I placed here so I'll get 15 points and so on. Yeah, experts say many a times that they feel that this position is strong and I need to take that position. Yeah, they just can't say why. And that's the knowledge acquisition bottleneck in Go. Yeah, the rule lives in an expert's intuition and cannot be written down. And this is where symbolic approaches had failed in the beginning, and we learned this in track B as well. And that's the two impossible problems that we just learned, that it's hard to solve. Yeah, there are too many moves to search, and there is no way to judge these positions and which position to approach. And that's the idea that AlphaGo solved for. Yeah, and they made a brilliant move by solving this. Yeah, instead of programming intuition, they said, hey, why not learn from it? And instead of searching everything, can we search intelligently? Can we calculate what's the winning move? And the problem was too big to search, that we just understood, and too intuitive to hand code as well. Yeah, AlphaGo's answer was to learn from intuition and keep the search. And we'll keep learning this in the second section. That's the two powers that they presented us with. And we as humans also do the same. We don't search everything. We by intuition know that, hey, we do not need to take a certain path, and we need to take a certain path. And AlphaGo just copied those into two networks. They built AlphaGo around the thought that, hey, you prune first and thin second. By prune first, we are saying how many steps, or what steps do you need to actually consider. And when we say think second, we are saying, hey, calculate the probability of success at that position. Yeah, imagine you're trying to solve a maze, yeah, that we looked at. We don't calculate every path. We instantly ignore the walls, and we say, hey, we have to go forward or backward or left or right based on the position we are in. Yeah, imagine finding a restaurant on Google Maps. It doesn't show us every road that's there. It surfaces, hey, take route A or route B or route C based on the traffic, the travel distance, avoiding road closures, etc. Yeah, and that's how humans we have learned over years. We have recognized patterns. We have said ignore the bad options and think deeply only about the good ones. Yeah, and AlphaGo just copied this into two neural networks. Yeah, one to prune and one to judge the position. The policy network is the one that learns by intuition. It says that, hey, look at the board and answer this question: which move deserves attention? Imagine if you had 250 legal moves, can you make all of them? No. What it does is, at that position, it says, if I can determine which move provides me the better probability of success, I will only pick those. And in 250 legal moves, it says move A has 48% chance, move B has 22% chance. Maybe I take only first two or first three, and so on. Yeah. How did it learn this? It learned from watching 30 million expert moves. It said, I'll watch the games of people who have made certain moves from the beginning till the end, and it calculate the probability at every point. It watched 30 million expert moves, not ordinary Go players, but the expert Go players, and it learned the strong players usually move here. They calculate the move A, move B, and so on. Yeah. In track B terms, this was the A stars move ordering, learned, not hand coded. We're gonna just quickly look at this in the next few slides, but it learned these from people who had made that move, and then it calculated the value network move as well. Yeah, it looked at the A board and estimated who's winning without playing all the 100 moves till the end. Yeah, it was calculating the probability of win at a particular position. What is my chance of winning versus my opponent's winning? Yeah, it was calculating at each point. And this is very similar to the house analogy. Imagine you're looking for a house. If a beginner goes and inspects a house, he will calculate too many things for 2 hours. But an experienced builder says, hey, within 30 seconds, I can say whether, hey, the plumbing is bad, the environment is bad, there are no hospitals nearby, there are no schools nearby, there are no good restaurants nearby, so I'll not buy. Yeah, that uh, that analogy is currently applicable here. And this is the heuristic A star that we learned earlier, right? Imagine the question that we were asking was, how good is this particular state? Yeah. Imagine at every point we want to move forward in the network and we use A star search. How do? We calculate the lowest possible score that we have, go there and look at the next possible lowest score, go there, look at the next possible score, go there, look at the next possible score until we reach the goal. Yeah, we always expand the node or travel in the node which has the lowest function score. And the function f of n was given by g of n and h of n, and g of n was the cost from the beginning till here so far, plus h of n. H of n is the heuristic estimate from that particular position till the goal. Yeah, approximate calculation. And whenever it was the lowest, it was taking that to reach the goal. Yeah, and this is what a star heuristic that it did for AlphaGo game as well. Yeah, it said to solve the problem of too many moves to search, I'll use a policy network. I'll not traverse across all the um, all the routes or all the paths to understand which one. I'll prune them. Yeah, how will I do? I'll learn from 30 million expert moves what is the right path to take. Yeah, and a star move ordering was learned there. Yeah, no way to judge a position. Is this position good? Is this position bad? How will I know? Yeah, that was solved by value network, estimating who's winning at that particular point in time. A star heuristic h of n was learned there. Yeah, and that's the founding lesson that we are applying as a strategy. Yeah, this brings us to very important part, which is Monte Carlo tree search. Yeah, the reasoning behind selective look aheads steered by the two networks. Yeah, it is typically done in 4 steps, and that's what we are going to learn. Yeah, MCTS, Monte Carlo tree search. So imagine you want to travel, you want to go on a vacation, and there are 5 or 6 list of places given to you: Japan, Italy, Canada, Australia, and US. Immediately your gut says Japan. Yeah, but before you confirm that you will be traveling to Japan, you will check your flights, your hotels, weather, budget, family's availability, and everything. Yeah, that's reasoning. Okay, and how is that reasoning done? Through intuition and search. Intuition, while intuition proposes a particular thing, your search verifies it. Yeah, and AlphaGo works the same way. The policy network proposes, hey, we'll take one path, one thing, and MCTS through search investigates each. Yeah, it never searches everything, it searches only the promising lines. Okay, and it is steered, as in it is selective in nature, it is deliberate in nature, it is not brute force. Okay, MCTS explores only promising lines. Okay, guided by the policy network where to look, and the value network, how good is this line. Yeah, this is what we learned in track based research as well. It's steered by learned functions instead of brute force. Yeah, imagine we start with our current position and we have these positions to take. Yeah, MCTS, since it has got the highest probability, it will go to A, and it will say, hey, this is the highest probability, let me take 55%. And it will go to A, then it will look at what's promising from here, next set of functions. Yeah, the tree only grows where it matters. If it, for example, BCD didn't matter here, so it dropped them, so it's only looking at A and A1, A2, A3. Yeah, so the tree is grown selectively, it's not picking everything. Yeah, biased towards good moves by the policy network instead of exhaustively. So we are not going through all the steps, we are only selectively taking certain steps. And it does evaluation at each of that step. A star heuristic, h of n calculation. Yeah, one prediction replaces thousands of simulated moves. At that point in time, it's calculating, saying that, hey, what are the chances of winning here? Instead of playing the whole game, it's asking the value network, what is my winning chance? Yeah, and that score is back propagated till the top, which is from move A. So far it hasn't made the move, it is only calculating at every step what are the chances of me going deeper and deeper there. Yeah, and that's where it back propagates and says that now that I know the calculations, I believe I'll make move A, because that has a 95% winning lift. Yeah, and next time AlphaGo trusts A bit more, and this is how it is learning through every step. Yeah, so what it does, it selects a particular node, it expands that node, it evaluates at each node, and then it back propagates. Yeah, thousands of time it does. So the search tree becomes a sharper and sharper estimate of the best move. And this is the whole thinking process that it took. Yeah, we look at Magnus Carlsen, why why it thinks in a similar way. uh, Magnus Carlsen also looks at current board. He looks at his policy network. He says, what are the good moves that I can make? He selects one, expands on that, and estimates, hey, can I win here going here to this position? And he updates the tree back till the current position, and that's the loop going back, and then decides whether it's the best move. Yeah. And Carlson also doesn't calculate every move. He sees this position, ignores the bad moves, studies a few candidates, imagines the future, chooses the one that will give him the best outcome. And AlphaGo just copied it. Yeah, they said, hey, PolicyNet will propose which route or which path to take. MCTS, which is Monte Carlo tree search, will calculate the winning probability. Yeah, we will value the net. Yeah, we will bring that valuation, and then we will take a decision. These are fast proposes and slow verifies. Yeah, fast proposes as in which network to take, slow verification as in reasoning out why we are taking certain step. Yeah, these are like the system 1 and system 2 that Daniel Kahneman had suggested, fast and slow. Yeah, in his famous book The Fast and Slow. Oh wow, this is all coming back now. Yeah, so you hold this, because once we go to week 5 or part 5, we will cash it in. We'll understand why we have to do so. Yeah, the intuition network narrows the search, and the search MCTS checks the intuition by looking ahead. Yeah, the result is better than either. Instead of doing either one, of a combination is really helping us. So the fast pattern recognition proposes, yeah, the slow deliberate search verifies it. Yeah, the pattern recognition which we did through 30 million expert goal learners, we are expert moves, we learned it from there. It tells what move to take. Now slow deliberate search calculates the probability of win. And this is the interesting part. So what all we learned so far is just two: policy network, value network. Yeah, how MCTS as value network is helping us uh, deliberate or uh, calculate the winning percentage and move forward. Yeah, now we know why there is a limitation in that, and how Alpha Go Zero overcame that, and test time compute is being built purely based on this. Now imagine we had to learn from humans, okay, by imitation, which is supervised learning. We know this. Yeah. How do we do that? If you had to learn guitar, what do? We first watch experts, and then we copy them. AlphaGo did exactly that. We just discussed that how 30 million expert moves were shown, and that it learned through their moves what is a good position. Yeah, each example became a pair. Board position, the move an expert player made until it could predict a pro would probably play here. Yeah, that's how it calculated the percentages there. So the board position to move was a supervised learning. This is the policy network head start. Okay, it got good at imitating strong human play, necessary, but as the next slide shows, it was not sufficient. Yeah, because there is a ceiling that we hit. Why? Imagine you only copy Michael Jordan. What will you become? You'll become a copy, because you'll never invent anything new. And that imitation inherits a ceiling, the best humans. Yeah, we cannot go beyond what human can teach. Yeah, and that brings us to self play or reinforcement learning, RL. You play, you start to play, you lose some of them, then you learn where did the uh, move that we make we lost, and then we play again, and we every time we keep improving in a loop. Yeah, now what AlphaGo did was it mimicked millions of games playing versus itself. So it became black on one side, it became white on one side. Yeah, and it started playing against itself. There was no human teacher here. The only objective that it was given, that you have to win. Yeah, this move helped it repeat it millions of times. And once it lost a particular game, it tried to avoid that particular move. Yeah. The payoff was that AlphaGo discovered strategies humans had never seen. Move 37 was one of them. In one of the games that AlphaGo played against Lee Sedol, I believe it is there in the next step. It's not there, but in one of the steps, in one of the games that I believe it was probably second or third game, that AlphaGo's Go engine played against Lee Sedol, it made a move which was number called move 37, and the commentator and the expert at that point in time said, "Hey, that's a move that nobody else would play." And after some time, they call the move genius because nobody or no Go player had played that move so far. But once that move was made, after a certain point in time, it became very evident that AlphaGo was going to win, and that move had made a, a, a big difference, and it became the well-known move 37 in the world of AI. So what AlphaGo did was it completely dropped the humans now, and it started from random. It said, "Hey, let me start from zero. I only have the policy network. That is, I only understand the rules. I don't have any examples, and I don't have any pro games. How will I learn?" Yeah, it started playing random moves, and it started playing with itself, and it started improving, and it repeated this millions of times. Yeah, random play, self play, learn, play better, and improve more. The result was this: AlphaGo 0 beat the original AlphaGo 100 to 0. Every game that AlphaGo 0 played, it won against AlphaGo. And that was the shock the humans and the whole industry received that day. And the lesson was this: yeah, human demonstrations were useful to get started, but not the upper limit of performance. Yeah, they became a ceiling. Just to reiterate, and that was the shock that was received. Okay, and we learned that humans became the upper limit for performance. Yeah. And in 2018 paper Alpha Zero, they generalized the recipe to chess and shogi, and they saw that AlphaGo Zero's logic was very intuitive, and it was winning over. So the complete AlphaGo pipeline and the PM headline should read as this: yeah, human games, policy network learns patterns, it self plays, and it improves the policy. Yeah, the value network learns the position quality, percentage of win. Yeah, using Monte Carlo tree search, and it's doing that using the best move at that point in time. Yeah, the lesson that outlives Go is this: yeah, while human data help to bootstrap, it capped the performance at the same time. Yeah, now removing it and letting the system discover the strategy from the first principles via self play produce something better than any human teacher could. Yeah, this was a seed for learn from outcomes or verification, not imitation. Do not imitate, learn from what outcomes we are trying to achieve through a verification. And this became the frontier reasoning model debate that started in 2026. Yeah, reinforcement learning from verifiable rewards. This brings us to the PM past plus lineage to 2026. Yeah, what we are going to look at is what was the result or the outcome of this, the four questions and one hard question that we could get in interviews, and why a board game paper explains the reasoning frontier. So when it played with Lee Sedol, the game was 4-1. DeepMind won 4 games. Lee Sedol won 1 game. Yeah, there were 200 million people watching it that point in time. And the move that we spoke about was in game 2. Thank God I mentioned it here. It was move 37 in game 2. Yeah, a move commentators first called a mistake and then called genius. Yeah, the machine found a strategy no human would play, and it was right. Yeah, that's a big thing. And this is the PM pass that we wanted to go through. Every time we read a paper, we want to understand 4 things. Yeah, what became possible because of AlphaGo, who productized it, or how fast it happened. Even bigger question was what died or what was disproven, and finally how is it being used in current environment, or what is being built for future. Yeah, what became possible? Solving problems too big to search and too intuitive hand code, that became possible. Yeah, how? By combining learned intuition with search. We used a superhuman strategy in a domain that thought it was a decade away. Yeah, people thought solving for AlphaGo was a decade away, and that became possible. Yeah, the game wasn't the product. Yeah, the recipe was. People understood that, hey, the game, mimicking the game itself wasn't the product. The recipe was, how do we solve problems where we need to learn on our own. Yeah, and that was solved using AlphaFold, data center energy. This is energy, by the way. Okay, data center energy optimizations, chip floor planning, and again a spelling mistake, and the test time compute paradigm behind 2025-26 reasoning models all came from this. Yeah, so much so that for AlphaFold, which is protein fold solution, Demis Hassabis received a Nobel Prize. Yeah, it was such a big discovery, and he made it open source as well. Yeah, what died or was disproven? Go is a decade away, is what people said. Yeah, and it was disproven. Human demonstration as a ceiling, it became zero. Pure brute force and pure pattern matching as standalone approaches will never work. We need to use them in combinations. 2026 descendant, everything that we do as reasoning or on reasoning models that take a lot of time to think is a descendant of this paper. Yeah, inference time search or compute, guided by a learned model, is from here. Yeah, AlphaGo was the patient zero on which this was tested. Yeah, the recipe, not the demo, was the product. Yeah, we need to be very aware of this, very cognitive of this. Yeah, AlphaGo's Go engine was near worthless because they didn't productize the whole thing. Its transferable method was the epoch defining, as in era defining. It's what changed reasoning forever. The PM Pass asks, what did this prove is possible? Yeah, this question. What was disproven or what became possible? Not what did they ship. Lesser on who productized it or how it was productized. Yeah. From a board game to the reasoning frontier, this is the thing that we see. In 2016, AlphaGo won. Yeah, it learned through Monte Carlo research, built on top of policy networks. Yeah, learned nets, beating Lee Sedol. AlphaGo Zero told us that humans were human data was the limitation. We need to go beyond that, and it beat the AlphaGo 100-0. AlphaZero took the same recipe to chess and shogi, and it also demonstrated the success there. Then came AlphaFold, yeah, where we were solving the protein fold problem. We'll look at this in week 12 as well, or part 12 as well of track key. Okay, and test time compute was solved using these. Yeah, because where we are saying more search or compute at inference time needs to happen. Yeah, reasoning models like DeepSeek's R1, ChatGPT's O series are all dependent on this. Yeah, the ultimate objective that we're going to learn is, hey, reinforcement learning plus inference time search on a language. Yeah, that's the outcome, and we'll learn more about this in week 11 as well. Yeah, the unchanging primitive that we are talking about is a learned model will propose search or extra inference compute refines it. Okay, training from outcomes can beat imitation. We don't want to hand code, build supervised learning models, teach these models how to learn. All we need to do is teach them the policy or guidelines and let them infer the outcomes. Yeah, the question to ask any reasoning model is, what's the learned intuition? Yeah, what's the search, and is it trained from human traces or from outcomes? Weaker on human traces, stronger on outcomes. That brings us to the last section, which is PM perspective. Yeah, why a PM will read this 2016 paper in 2026, and some misconceptions to kill, of course. Yeah, so here are some important topics that we should take away as PMs from this paper. Yeah, So you can read the reasoning model era papers, yeah, but AlphaGo will be the origin, yeah, of test time compute. Yeah, what it did was it learned intuition and search and trained on the outcomes. Yeah, and that lets you evaluate 2026 reasoning model claims. Yeah, you understand the cost, you understand that hey, inference search means more money. You have to do lot of search means more money. Instead of doing lot of search, can you prune that search? Yeah. The second point is sometimes the recipe, not the demo, is the product. AlphaGo's engine was not making any money at all, but the recipe that it built, the intuition plus search, that caught up. Yeah, and we as PMs need to catch that value. The third was people saying hey, it's a decade away, as in AlphaGo problem to be solved is a decade away, is what they said. It wasn't a fact, it was a signal, but it was demythed in approximately a couple of years. Yeah. So the most cited misprediction in AI history, be skeptical of these confident people saying AI can't do X for years. Yeah. We need to have our own roadmap of assumptions and keep validating them every time a research paper releases. Yeah. And self play will always beat imitation games. Yeah, imitation is good to begin, but self play will always beat it. We need to learn from outcomes and not from copying humans. That's the frontier training debate that we are currently in, and zero was a proof of concept for that. Here are some misconceptions to avoid. AlphaGo was just brute force search. Brute force is impossible in Go. We just learned it's 250 to the power of 150 number of combinations or moves that you can take. It's very hard. So AlphaGo was not just brute force. It was pure deep learning. It was deep learning plus MCTS. Yeah, through Monte Carlo tree search, we understood how we can prune the search, reduce the search, and calculate the probabilities and win at every step. The human training data was essential. AlphaGo 0 completely dropped it. It started from random stage and 100 on AlphaGo. Yeah. So while data that was given by humans bootstrapped it, it capped the performance also. Yeah. A board game result is irrelevant to LLMs. It is actually the origin of test time compute, inference on the fly. That's purely happening because of this. Large reasoning models, you are using it as the core of their reasoning. Yeah. AlphaGo could do other tasks. The system was Go specific, okay, but the recipe that was built was generalized. Alpha 0, Alpha Fold. Uh, we need to learn how to distinguish the demo from the method. Yeah. So typical interview questions that we are going to be asked is why was AlphaGo a landmark? Firstly, it cracked Go because Go had 250 branching factors and handwritten evaluation functions was hard. So brute force and symbolic approaches both failed. And what AlphaGo did was it learned a policy network and a value network. Policy network told it which moves to consider, and a value network told it how each of that move is winning. Yeah, and then we used MCTS to steer ahead as a value network. Okay, so it beat Lee Sedol 4-1, and that's what AlphaGo did differently. Yeah. How do the policy and value networks map to classical AI? Very simple. We looked at A star heuristics on how it's doing. Policy network is typically A stars move ordering, uh, which in which order do I need to select. Once it has selected a particular a point or position, we need to evaluate. Yeah, and that value network is the learned evaluation function, which is h of n. Yeah. What's the significance of AlphaGo 0 beating AlphaGo? Because this was completely human-less training, as in there was no human supervised data given to learn here. It started from scratch and it randomly played, it understood the rules, and then it played it played the games against itself. It did reinforcement learning and it beat the human strap bootstrapped version, which is AlphaGo, by 100-0. So the lesson that we need to learn here is that, hey, learning from outcomes can exceed the imitating humans. Yeah, that's the biggest lesson that we can learn from here. How did AlphaGo connect to 2026 reason models? The origin of test and compute in real time is coming from this. Yeah, AlphaGo spends inference time search guided by learned networks to play a better move. You know, reasoning models like R1 and the O series are spending inference time compute to think before answering. Trained are trained with RL, much like AlphaGo's self play. Yeah, same primitive. A learned model proposes, search or compute refines it. Outcome based training beats imitation, and it's why these models cost more per query. Why the recipe, not the demo, is the key PM takeaway. Yeah, AlphaGo's literal product, that Go engine that we looked at, had no commercial value. Yet the paper itself was epoch defining because it proved a method that worked, and it learned from intuition plus search and trained from outcomes. Yeah, it didn't train from the actual human moves. It learned from outcomes. Hey, if I move here, what will be my probability of winning? It calculated on its own. It played against itself, and that's why it becomes very very different. Instead of asking what did this paper build or what did the AlphaGo build, the PM, intelligent PM, asks what did this prove is now possible. That's the entire recipe. Yeah. And this was the vocabulary that we learned. Why Go was hard, the architecture, policy network, and the value network. How MCTS was used to steer look ahead, which is select, expand, evaluate, and back propagate. Training arc that we learned. Initially it imitated, but then started doing self play games. AlphaGo 0 beat AlphaGo by 100 0. You know, and Alpha Zero played chess and shogi as well by self learning or reinforcement learning. Lineage, we saw AlphaGo 0, Alpha 0, AlphaFold, test and compute into reasoning models. We looked at the test that we performed was purely learning H of n, yeah, and steering the search and then dropping the humans. This is all connecting it back to 2026 reasoning models that are using test and compute. Yeah. Uh, the learned intuition plus deliberate search are the two words or two phrases that we should take away from this. Yeah. One commentator who said it on the 37th move, hey, it's not a human move. I've never seen a human play. That was the goosebump moment. Yeah. Rich Sutton in the bitter lesson said that, hey, general methods that leverage computation are ultimately the most effective. Leverage computation, general methods. Yeah. So that was Tracky Part 2, the AlphaGo as paper. The paper's name is Nature, published in 2016. If you're more interested, go watch AlphaGo video that exists in YouTube. Thank you.